Welcome everyone, I'm Lucas. I'm currently a postdoc at NSI, and this is intended to be an extended presentation of the talk I will be giving next week in the EAAE conference. So the talk is entitled Statistical Inference in Large Multi-Way Networks. It's a joint work of myself with Guillaume Lequet, Lionel Wiener, and Philippe Chonet, everyone here at NSI, except for Guillaume, who is in ESSEC. So our motivation here is to perform network estimation. So we care about estimating a structural parameter in a network. We focus on weighted multi-way network. So besides only looking at the extensive margin, we look also in the intensive margin, and we consider that the edges of this network, they can contain non-negative integers. So it's a counter you can think of. And we also consider multi-way networks. So we can, the method that will be described here can be used for two-way, three-way, four-way, D-way networks. And the main issue here is the presence of nuisance parameters. So we consider that each node you can think of has a fixed effect. We don't care exactly about the structure of the fixed effect. The method will be agnostic to this structure. But what's important here is that the maximum likelihood estimator, that is the PPML estimator, suffers from the incidental parameter problem in this context. So due to the presence of the nuisance parameters, the estimation of the structural parameter has some bias. And besides all of that, we also want to have some solution, some method that is computationally feasible, mainly in sparse, large data sets that appear in applications, mainly in social sciences. So, just to be clear, we stick here with the classical model in the gravity literature. So we model the intensity of each node as a Poisson with this with a log intensity in this form here. Of course, for clarity in this presentation, I will stick with the two-way case, but everything that's going to be said here generalizes to the multi-way case. And also, we have implemented the method for the multi-way case. It's really just for simplicity in presentation. So it is well known that the sufficient statistics for each fixed effect is just the generalized degree, in the sense, for instance, that in the two-way model, if I have, for instance, patients and doctors, the sufficient statistic of the fixed effect of a given patient is simply the sum of all y's associated to this patient. So I will denote by delta, then the delta I, alpha I, is the fixed effect associated with individual I. It's just the sum on all the other coordinates, so j here, the doctors, of yij. And the same hold for the doctors. So the sufficient statistics for the fixed effect of a given doctor is just the sum of yij, j is the doctor, over all i's, over all patient I. I will also denote by delta, without any super or subscript, the sufficient statistic for all fixed effects, for both patients and doctors here, or in other words, for i's and j's. There is this well-known conditioning trick that if you have a maximum likelihood and you condition on the sufficient statistics for some parameter, the probability that you obtain does not depend on this parameter. So if we condition on the degree of y being equal to some given degree, the remainder probability here, the thing that remains here, does not depend on the fixed effects. So this is just a function of the structural parameter beta. This is a well-known trick, quite used in the literature. But the thing here is, in order to do that, we need to understand the set. We need to know for a given network which are all other networks that has the same degree, the same sufficient statistics. So we can map this set here. So in the end, we want to take a graph and we want to find all the other graphs, all the other networks that preserve the degrees. In the two-way case, it means that we want to preserve the sum of lines for all lines and the sum of columns for all columns. If I start with some network and I want to make some other network, I need to change at least one entry. Let's assume that I will change the first entry. So in this example, I change this 5 by adding 1. Therefore, I will end up with 6 here. But I need to preserve the sum of the first line. So if I added 1 somewhere, I need to subtract 1 somewhere else. I will subtract 1 here in this 2. But now, since I subtracted 1 in this 2, I need to sum 1 somewhere in this column. I will sum 1 to the 4. And since in the beginning I added 1 to this 5, I also need to subtract 1 somewhere here in this column, the first column. I will subtract from this 3 here. So you see that we got these sign patterns here, and we end up arriving at some new network that preserve the same degrees. And I can do the same procedure with this new network. Now I select some other initial edge to sum 1, and then I need to subtract and sum to make sure that the degrees are preserved. And so all these networks, this first one, this intermediate one, and this last one, they all share the same sufficient statistics for the fixed effects. Just to put some notation, I will call this matrix of signs here S. I call this transformation of taking a y and summing this matrix S by T, and I will parameterize all these transformations, or the same way, I will parameterize all these matrices of signs S using what we will be calling here a polyad. So a polyad in this example here, C1, is just a pair of columns, a pair of lines. If you are in a three-way, you also have like a pair of the third dimension. Then if you're in a four-way case, a pair of indexes in the fourth dimension, and so on. So here, for instance, this guy is saying that I'm taking the first and the second lines, and also the first and the second columns. So first and second line, first and second columns. And here, in this other example, I take the second and the third lines, and I take the third and the second columns. So second, third lines, third and second columns. Notice that I could also say that I'm taking the second and third column, but there is a small notational observation here that the order will tell me where the positive sign starts. So if I do 2, 3 instead of 3, 2, then the positive sign will be here in the first edge. Otherwise, it will be here. So it's just a convention to say where the positive sign will be. And as it turns out, these transformations, they characterize fully this procedure of degree preservation. So if two networks share the same exact degrees, so that is, if I have y and y prime and delta of y is equals to delta of y prime, then there exists a finite sequence of polyoids, that is, of indices, of pairs of indices, and integers r1 to rm, such that y can be written just composing these transformations. Notice that I can take r to be negative. In this case, I'm just composing the inverse transformation. So what we propose here then is to first to observe that this characterization let us understand this set here. So the set of all networks y that have the same degree as some small y here is just that. So it's all the y's that can be written that way. And notice that here we have we can start with some polyad, operate a few times the transformation given by this guy, then move to another polyad and operate a few times the transformation given by this polyad, and so on. What we propose here is, since this set here is quite big, because we have a lot of freedom composing these polyads, we propose to remove this composition, oirons, and instead to look at each polyad a time in the direction that the polyad gives. So we compose the transformation of a polyad as much as we can, but only of a single polyad. And then we do that and we sum this log likelihood over all polyads. So we replace this this log likelihood by this function here. And doing that, what we end up having is a logistic regression defined for each polyad. To exemplify what's happening here, take this graph. So here I have some 3x3 two-way network denoted as a matrix, and I will take this polyad that involves lines 2 and 3 and columns 1 and 2. So here I just have y. If I compose 0 times, I end up having the same guy as in the beginning. Now, if I do the operation, create the operation parameterized by this polyad once, I will sum 1 in this 3, subtract 1 in this 4 here, subtract 1 in this 1, and sum 1 in this 1, end up here. If I do the transformation, the inverse transformation, I subtract 1, sum 1, sum 1, and subtract 1, and end up in this graph here. But the interesting thing is, if I apply the transformation many times, in this case, if I apply the transformation 2 times, I will eventually get a negative number. And the same holds in the other direction. If I apply the inverse transformation many times, enough times, I will end up again with a negative sign. And the interesting thing is that the Poisson likelihood gives probability 0 for these graphs. And of course, if I keep going, I will get, again, other networks with negative sign. So there's no reason to keep going. Meaning that for a given graph and for a given polyad, I have a logistic over a finite set of options. And indeed, this logistic that we get has this utility here. So given a polyad and of course given a graph, the utility of the graph that you obtain applying the transformation r times is given by r times beta t x tilde xi minus some entropy penalization. And this xi prime here, it's just GIF and GIF, basically, of the covariates of the edges involved in this polyid. So basically, we have here in this first term an structural payoff that wants to shift as many connections to edges with signs similar to the one of this GIF and GIF here, and we have some entropy penalization that wants to avoid putting most connections in few edges. And this is quite similar to the differencing vector that one can find in this nice work from Danu, Bonoré, and Martin Weidner from 2025. Of course, the math works, meaning that, first of all, we have a very nice laws that is strongly convex and has nice convergence guarantees using Newton method. We have consistency, and we also have asymptotic normality. And we notice that since we have consistency and we have asymptotic normality without bias, we don't have the incidental parameter problem here. Sorry, we have solved the incidental parameter problem that the PPML has. So it remains now just to understand how to compute this loss. The first approach that one could have is the naive approach, which is just to generate all possible polyods and evaluate the loss in each polyod. So evaluate the logistic given by each polyod. The problem is, if one wants to do that, and we have here a D-way model, you need to find a pair of indices of the first index, a pair in the second, up to a pair in the diff coordinate. Therefore, you will have something of the order n to the square, where n is the total number of possible edges in your network. And this is not good, because this is quadratic, and PPML, for instance, runs in linear time. So, of course, we don't want to have a quadratic algorithm. It would not be feasible in practice. It would be even worse in very large networks that we can find in practice. So we need some solution to this problem. And the solution came first by observing that not all polyods are informative. Indeed, there are some polyods that if you try you take a graph and you take some polyod, there are some polyods that if you try to apply the transformation, you will immediately arrive at some network with a negative weight, with a negative, negative weight in both directions. So this polyod has only one choice, this logistic has only one choice, and of course it will choose this. Therefore, this is not informative. When we sum the likelihood, the log likelihood is 0, so it adds nothing to our optimization. So it would be very nice to skip these non-informative polyods. And one can stop and think a bit about that, but it's quite easy to see that for a polyod to be non-informative, it suffices for the minimum of the guys associated with sign, with positive sign, and the minimum of the guys associated with negative sign to be both 0, which is the case here. So we have here associated with the positive sign, we have 0 and 0. The minimum between 0 and 0 is 0. And associated with the negative sign, we have the minimum of 4 and 0, which is 0. So the problem here is, imagine that I want to sum 1. In order to sum 1 to the 0, I need to subtract 1 to this other 0. But if I subtract 1 to the 0, I end up with a non-valid network, and the same happens in the other direction. And besides that, we also explore the fact that two different polyods can define the same logistic. So, for instance, here I'm taking a polyod with lines 1 and 2 and columns 2 and 3. If I just flip the lines to be 2 and 1, I will flip the signs. So going forward here will look like going backwards here, and going backwards here will look like going forward here. But in the end, the classification problem that we have is the same. The logistic is the same. So there is no need to go over all these permutations. We can always pick only one permutation. And then the proposition here is that every informative polyod Kc has a permutation that will satisfy this. So for it to be informative, we need the minimum of the positive signs or the minimum of the negative signs, at least one, to be bigger than 0. Since we can always have these permutations and they flip the signs, we can always ask for this specific minimum here to be bigger than 0. And for this minimum to be bigger than 0, we need to have two edges in our network that are non-negative. So we just need to loop over all pairs of non-negative edges. This is quite interesting because, for instance, if you have a sparse network in the sense that most edges are 0, it may be the case that looping on the pairs of positive edges has a much smaller cost than looping over pairs of any kind of edge. And now we have some experiments. This first experiment, we look at a very small data set, and we care about density. So we will see that so here in the x-axis, I have the density of the graph. I have here PPML debias, which is the analytical debias proposed by Zielke and Weidner for PPML. We also have here our polyods method. And what we see is that at very, very low densities, PPML and PPML debias, they tend both to not have a nice coverage and also not to converge. Meanwhile, our method behaves much better even at sparser graphs. Of course, as the graphs get denser, all methods start to be more or less comparable here. Mainly the PPML debias is quite interesting in this case. Now I will see a sparse example. So I will say that the number of positive edges will be 4 times the square root of the total number of edges. And I'm also considering here a negative binomial distribution, just not to always stay with the Poisson distribution. And here we see that the PPML has some bias. So the error should be 0, it's 0.5 and quite consistent at 0.5. We see that the analytical debias indeed reduce the bias, but do not remove the bias completely. We see that our polyods method seems to be unbiased. And of course, we see here that we hit the 95% coverage quite well. PPML starts with a higher coverage and the coverage decays, and PPML is quite bad without the debias. I have also examples for the four-way case, just to show. In the four-way case, unfortunately, we don't have a analytical debias method, so I'm comparing PPML against polyods, and we see more or less the same. The polyods method has some nice, it's quite consistent at 0. PPML has some bias. Our coverage is quite close to 95%. Meanwhile, PPML degenerates fast. And to finish the experiments, I also have here an example of a zero-inflated experiment. So here, what I did was to generate the data following a Poisson distribution in a sparse case with n equals to around 3 million. And what I did here was to go at random in the network and turning the random entries to 0, which is the same as sampling from a zero-inflated distribution. Here we see in the x-axis the probability of deletion, okay? And we see that both PPML and PPML debias, they, as we increase the probability of deletion, their error increases. Meanwhile, for the polyods method, our variance do increase, but we stay centered at 0 here in the error. Our coverage also stills quite nicely at 95%. Meanwhile, PPML coverage is at 0 and the debiased version is decaying. And also, we see here in this last graph on the convergence, we see that PPML tends to converge in more samples than PPML and PPML debiased. Although, if we have a high proportion of zeros, a high amount of zeros, we start to find examples where even the polyods method does not converge quite well. Just to summarize now the main contributions, first we have a multi-way method that works for any structure of fixed effects. So it's multi-way in the sense that it works for two-way, three-way, four-way, six-way, any way you want. It supports any structure of fixed effects. So for instance, if you are in a three-way case, it will work if you have fixed effects like alpha, so three-way, imagine index ijt. If your fixed effects are alpha ij plus gamma it plus xi jt, it works. If it's alpha I, gamma I, alpha I, gamma j, and ct, it also works. So the method is agnostic to the fixed effect structure. Indeed, it's faster on sparse networks when compared to PPML. We have no asymptotic bias by construction. We have an interesting loss function with good convergence. Our confidence intervals are reliable, at least under model assumptions, but also as we deviate, as we see in the negative binomial, we have experiments showing that it's also reliable. In the zero-inflated case, it's also reliable. I also have a Python package implementing this method, which can be installed through pip-install polyads, and the computational implementation provided by our method works for any polyad-based method. So, for instance, there is some literature on the two-way case using tetrad-based methods. Jockmans has some interesting GMM estimator. There is also literature for the three-way case on XSAT-based methods. For instance, the paper by Maris and Peckel. Also in the two-way, we have the classical network formation paper by Graham. But I guess that the main message here is that our method enables inference in very large, sparse data sets that would not be possible with the methods that are currently available.